We've all seen them, right? These high-speed trains just slicing through the landscape like something out of science fiction. They are absolute marvels of engineering. But what you don't see is the invisible and, honestly, incredibly violent battle that's being fought right underneath them. It's a war between the train and the very steel tracks it's riding on. So today, let's dive into this hidden world of extreme mind-bending physics. So the big question is, what is this invisible force? I mean, we're not just talking about weight or friction in the way you'd normally think. No, this is something way more fundamental. It's a threat that's pushing our material science to the absolute brink, a force that could literally tear these incredible machines apart, starting right from the rails they run on.
Okay, so to really wrap our heads around this threat, we've got to look at the brand new generation of high-speed prototypes. And these aren't just, slightly faster trains. They are so ridiculously fast that they're forcing engineers to go back to the drawing board and completely rethink the basic science of something as simple as a wheel on a rail.
So, you've got two main players in this game right now. On one side, there's China's CR450. Get this. It's already hit a test speed of 453 kilometers an hour. That is just staggering. And then on the other side, you have Japan's Alpha X, which is basically a rolling laboratory, built to perfect travel at a cool 360 kilometers per hour. Now, both of these are obviously masterpieces, but their insane speeds are creating a problem that's way, way bigger than just cutting through the air. Yeah, forget about aerodynamics for a second. The real war zone isn't in the air around the train. It's happening at the atomic level, down in those two thin, shiny ribbons of steel that have to somehow, against all odds, survive forces that, honestly, should just obliterate them. So how does this happen? Well, it all boils down to the cold, hard, and really unforgiving math of kinetic energy. See, at these kinds of speeds, the train's velocity stops being just a number on a dial. It becomes a weapon aimed squarely at the track. You probably remember this from high school physics, right? Kinetic energy, it's 1/2 mass times velocity squared. And that little squared at the end, oh man, that's everything. That's the whole ballgame. Because it means the destructive energy blasting into the track doesn't just go up with speed, it goes up exponentially. And this is where it gets crazy. Just look at what that exponential jump actually means. When you go from 300 to 450 kilometers an hour, which, is a 50% speed boost, you're not getting 50% more energy. No, you are more than doubling the kinetic energy that's pounding into those rails. The track has to somehow soak up this absolutely massive and totally disproportionate jump in destructive power every single time a train passes. So where does all that energy go? Let's zoom right in. All of that incredible destructive force is focused on one tiny, almost unbelievable spot, the wheel-rail contact patch. This is it. This is where the giant world of the train slams into the microscopic world of atoms and metal. I want you to really picture this. You've got a machine that weighs hundreds and hundreds of tons, and it's moving faster than pretty much any land vehicle you could possibly imagine. And all of that weight, all of that kinetic energy is being funneled down into the earth through a tiny little patch on each wheel that's no bigger than a coin. The pressures are just astronomical. There's really no other word for it. And this quote just nails it. At these speeds, that little contact patch, it's not just a mechanical surface anymore. It literally transforms into a high-energy thermodynamic reactor. I mean, think about that, a reactor. A place of unbelievable pressure and heat where the normal rules of physics are just being stretched to their absolute breaking point. So this high-energy reactor, it's waging a two-front war on the steel. And the first front is all mechanical. It's just a relentless, punishing war of attrition. And this war actually has a name. It's called rolling contact fatigue, or RCF for short. The best way to think about it is like death by a million tiny cuts. This is the #1 reason high-speed rails wear out. Every single wheel that passes over is one more punch, one more stress cycle that makes the steel just a little bit weaker. So here's how it goes down. Step 1, the sheer stress from a wheel pass actually deforms the steel. Now, after millions and millions of these little deformations, the steel just gets tired, it loses its flexibility, and tiny little microcracks start to form. Then, those cracks grow and spread with every single train that goes by, until finally, they connect. And when they do, whole chunks of the rail can literally just break away. And we're not talking about a little bit of wear and tear here. This is serious stuff.
It leads to failures like spalling, which are basically like huge, jagged potholes forming in the steel, or squats, which are these dark depressions that create a violent hammering effect on every single train that flies over them. Both of these cause insane vibrations and, as you can imagine, dramatically jack up the risk of a derailment. But believe it or not, that mechanical beatdown is only half the story. The second front in this war is, well, it's even sneakier. It's a thermal process, where the crazy amount of energy from the train actually forces the track to create its own worst enemy. Okay, so even at 400 kilometers an hour, the wheel isn't perfectly rolling. There's always a tiny, tiny amount of sliding friction happening in that coin-sized patch. It's called microslip. And this microslip generates an absolutely insane amount of heat. We are talking about instantaneous temperature spikes that can hit 1400 degrees Celsius. That is hotter than molten lava. So you get this microscopic inferno, which is then immediately followed by a self-quenching, because the rest of the massive cold rail just sucks the heat away instantly. In this process, flash heat, instant cool, it forges something entirely new on the surface of the track. It's called a white etching layer. And folks, this is the real villain of our story. So what's so bad about this stuff? Well, just look at the difference. Your normal rail steel, it's strong, but it's also ductile. That means it can bend a little under pressure before it breaks. It's got some give. But this white etching layer, it is extremely hard, yes, but it is also incredibly brittle. It has zero give. It shatters, just like glass. And that right there is the killer problem. The train is literally creating, in real time, a razor-thin layer of glass on top of its own steel track. So what happens next? Well, under the relentless pounding from all the other wheels, this brittle layer fractures almost immediately. And in doing so, it creates the absolute perfect starting points for those catastrophic cracks we were talking about earlier. I mean, this quote just sums up the whole thing perfectly. The train's own massive kinetic energy is literally weaponizing the steel against its own structural integrity. The train is forcing the track to destroy itself from the inside out. It's just mind-boggling. You know, we look at modern high-speed trains and we see these symbols of just effortless progress. But what if I told you that that seamless performance is actually built on a foundation of spectacular and often terrifying failure? Well, this is the secret history of how engineers discovered the brutal, brutal limits of steel, the hard way. So our first lesson takes us all the way back to France in 1955. This was a really ambitious attempt to prove that, you know what, sheer power alone could conquer the laws of physics. Spoiler alert, it couldn't. Okay, so get this. On March 29, 1955, a specially modified electric locomotive, the BB9004, hit a speed that was just staggering for the time, 331 kilometers per hour. In the mid-1950s, this was almost science fiction. It was a world record celebrated across the globe. But that celebration, well, it was very, very short-lived. The moment, the very second, the driver cut the power right after setting that record, all that immense kinetic energy unleashed this terrifying phenomenon called bogey hunting. And this wasn't a gentle sway, okay? This was a violent, totally uncontrollable side-to-side slamming of the train's wheels against the rails. The sheer force coming from the locomotive's wheels it's hard to even imagine. The steel rails, these things designed to be perfectly rigid guides, they just started to physically deform under the stress. They twisted and they warped out of alignment almost instantly. And in just a matter of seconds, a continuous stretch of 500 meters of track, that's half a kilometer, was utterly destroyed. It was just rendered completely impassable. The forces were so extreme that the infrastructure basically disintegrated. And if that wasn't dramatic enough for you, the incredible electrical draw and friction completely melted the locomotive's rear pantograph, that's the arm that connects to the overhead wire, and it showered the roof of the train in molten metal. Just unbelievable. So the crucial lesson here was a really harsh one. It didn't matter how much horsepower you gave a train. It meant nothing if the steel infrastructure underneath it was fundamentally incapable of surviving the journey. Brute force had totally and completely failed. Okay, next up, we're heading to Japan. And this lesson, it wasn't about a single explosive event. Oh no, this was a slow, agonizing war of attrition against the steel itself. To the world, Japan's Shinkansen, the bullet train, was this futuristic symbol of absolute clockwork precision. But behind that incredible public image, the network was fighting a silent, agonizing maintenance crisis that was threatening the entire system. So when the first line opened back in '64, its speed of 210 kilometers per hour was revolutionary. But by the late '60s, the rails, which were just conventional steel, were failing at an absolutely alarming rate. It got so bad that by the early '70s, the only thing preventing catastrophic derailments was this massive, incredibly expensive, and nonstop rail replacement program. And here they are. These were the culprits. The steel was suffering from something called high cycle fatigue. Essentially, the constant, unyielding pounding from the trains was causing the rails to develop these ripples and deep pits, and even worse, these internal cracks called transverse fissures, flaws that could just grow completely unseen until the rails suddenly and catastrophically failed. So, if 1955 was about brute force and the 60s were all about endurance, our next lesson takes us back to France in 2007. And this one was about finding the absolute, final, physical limit of a steel wheel on a steel rail. On April 3rd, 2007, a heavily modified TGV train set a new record that was it was earth-shattering. 574.8 kilometers per hour. That's almost half the speed of sound on conventional rails. But as you can probably guess, this was no ordinary journey. And this slide just perfectly shows how extreme this whole thing was. I mean, to hit that record, they used extra large wheels, they boosted the train to 25,000 horsepower, and they cranked the voltage in the overhead lines up to 31,000 volts. This was a machine pushed to the very, very brink of disaster. And what did that actually feel like? Well, reporters who were on board said that by 540 kilometers per hour, the energy transfer between the wheels and the rail was so violent, it was nearly impossible to even stand up inside the train. The entire system was literally on the verge of shaking itself apart. So these experiments, they pushed the limits. But sometimes the limits push back, and with absolutely tragic consequences. Our final lesson is the most solemn one. A reminder that these incredible forces have life or death stakes. For this, we have to go to Germany in 1998. 101 people lost their lives in the Eschwege train disaster. It remains this dark, unforgettable reminder of what happens when high-speed metal fatigue goes unmanaged. Now, in this case, the failure didn't start in the track. It started in a steel wheel. But here's the crucial point. The physical mechanism was the exact same threat that was facing those Japanese rails, a tiny, unseen crack growing silently through a critical steel component, all under the incredible stress of high-speed travel. This slide just lays out the whole catastrophic chain reaction. A microscopic crack forms from just normal wear and tear. It grows silently. Then, all of a sudden, the wheel tire just shatters. The train derails at 200 kilometers per hour and slams right into a bridge. A tiny metallurgical flaw scaled up into a massive, macroscopic catastrophe. So what's the big takeaway from all of this? What do we learn? All these stories of twisted track and shattered wheels, they all point to one central, unsung hero of the high-speed rail story, the unseen science of steel. These failures, they taught us everything. France in 1955 proved that raw power is useless without robust infrastructure. Japan's agonizing grind in the 60s and 70s revealed that high cycle fatigue is this relentless, silent enemy you have to fight every single day. The V150 record run showed us the hard physical limits of the entire system. And Eschwege was the tragic, ultimate reminder that a microscopic flaw can become a macroscopic disaster.
I mean, we all know that classic train sound, right? That rhythmic, kind of violent, clack, 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 clack. And even early high-speed rail wasn't much better. It was unstable, always breaking down. But today, the networks that support trains like China's CR450 or Japan's Alpha X, they're just in a completely different league. They're silent, they're flawless, and they're unbelievably smooth.
But here's the thing that gets me. The basic laws of physics, friction, vibration, stress, none of that has changed. A giant metal box screaming along a metal track at hundreds of kilometers an hour should be a chaotic, noisy mess. So what's going on? How is this quiet perfection even possible? Well, the answer isn't something you can see on the surface. It's happening deep down, at the molecular level of the steel. This is the result of decades of absolutely obsessive, painstaking refinement in metallurgical engineering. The steel rail isn't just a dumb piece of metal anymore. It's a highly engineered, almost intelligent structure, designed from the atoms up.
Okay, so to really appreciate this new super steel, we first have to understand what came before it. Let's take a quick look at the limits of just regular old conventional rail. So your standard old-school train track is made from a pretty straightforward steel alloy, something like this U71Mn grade. Its whole job was basically to just be strong enough to handle heavy freight cars and passenger trains that weren't going all that fast. It was built for brute strength, and that was about it.
And if you look at the recipe, it's super simple. You've got carbon for your basic strength and manganese to make it hard. That's really the whole story. It's a workhorse for sure, but it's a sledgehammer. It has none of the finesse you need for today's incredible speeds. Now just imagine trying to run a 400-kilometer-per-hour train on this stuff. The forces would be insane. It would literally start to tear the steel apart. You'd get what's called plastic deformation, which is just a fancy way of saying it would bend and then stay bent. The track would warp itself into junk, and eventually you'd have a catastrophic failure. It's just not even close to being up for the job.
So that brings us to the first of our modern solutions, and this one comes from China. We're going to look at their recipe for resilience, the very steel that was forged to make the groundbreaking CR450 train a reality. See, instead of just focusing on basic strength, China's engineers went for toughness and extreme wear resistance. Their main weapon is an alloy called U75V, and its secret is a tiny dash of a very special ingredient.
And that secret ingredient is vanadium. The way it works is just brilliant. First, you add a teeny tiny amount. We're talking less than 0.12% into the steel mix. This vanadium bonds with carbon and forms these unbelievably hard microscopic particles. These tiny particles then act like little roadblocks inside the steel's crystal structure, physically stopping it from shifting around under stress. And the result? An exponential jump in how well the rail resists wear and tear.
You can think of it like adding microscopic rebar into concrete. It's this incredible nanoscale reinforcement that lets the steel just shrug off the kind of kinetic impacts that would absolutely pulverize standard steel. It's such an elegant way to solve the problem.
And for the really tough parts of the track, the high-stress zones like sharp curves, they bring out the premium stuff. They use an even tougher alloy called U78CRV. This one adds chromium to the mix, which helps create an even finer, denser structure that stops the very surface of the rail from disintegrating under the most extreme pressure.
But wait, that's not the only way to do it. Let's pivot now and look at Japan's totally different philosophy. For their Alpha X project, they follow what you can only really call a purity doctrine. It's a fascinating contrast.
So while China is adding special ingredients to create strength, Japan is obsessed with taking things away. Their entire strategy is built around one goal: achieving absolute, hyper-pure steel with basically zero imperfections. The enemy, in Japan's eyes, are these things called non-metallic inclusions. Now, these are just microscopic impurities, little bits of junk like alumina or silicates that are a natural part of making steel. But here's the problem: even though they're tiny, they are the exact starting points for catastrophic failure. They're the weak links.
So you might ask, how many of these tiny little flaws are acceptable in Japanese high-speed rail steel? The answer is staggering. The target is almost zero. This demands a manufacturing process that is so unbelievably clean and precise, it's been optimized for decades just to eliminate any chance of an internal flaw. So why this obsession with purity? Well, because these little inclusions are hard and brittle, they become tiny points where stress gets concentrated. They are the literal birthplace of fatigue cracks, the tiny fractures that grow over time and eventually destroy the rail. So if you can eliminate the inclusions, you basically neutralize the risk of the rail failing from the inside out.
Okay, so you can have the most perfect, toughest steel in the world, but it's still going to make some noise with a high-speed train running over it. The final piece of this puzzle is actively designing for silence. And for that, you have to look at the entire system, not just the rail. Now, here's a really surprising fact that most people get wrong. You'd think that whoosh sound from a high-speed train is mostly the sound of it cutting through the air, right? Aerodynamic noise. But it's not. The biggest source of noise is actually something else entirely.
The real source of the sound is the interaction between tiny, microscopic bumps and dips on both the wheel and the rail. At these insane speeds, those little imperfections make the entire track vibrate like a giant, miles-long guitar string, and that vibration is what you hear.
So how do you silence a guitar string that's hundreds of kilometers long? Well, first, you get rid of what's plucking the string. Modern tracks use what are called continuous welded rails. They are seamless ribbons of steel that completely get rid of those old expansion joints that made the clack-clack sound. Then, you attack the vibration at the source, on the train itself. The wheels are housed in these enclosed bogies with incredible cushioning systems that absorb impacts before they can even get into the rail.
And for any vibration that still gets through, you add these things, rail dampers. They're basically acoustic shock absorbers that bolt right onto the rail. They grab all that high-frequency vibration energy, and through internal friction, they convert it into a little bit of harmless, low-grade heat. The result is a massive reduction in the sound that actually makes it to your ears.
So when you put it all together, the nanoscale reinforced super steel, the obsession with absolute purity, the continuous welded tracks, and all the advanced damping systems, you get the final result. A completely seamless, whisper-quiet glide path, even at an incredible 450 kilometers per hour. It's truly a symphony of engineering.
All right, so let's just run with that idea for a minute. If we were going to design the perfect rail based on hardness and hardness alone, we'd be looking for a real super steel. And, well, metallurgists actually have one.
Meet martensite. This stuff is just fiercely hard. The way you make it is by taking hot steel and cooling it down so incredibly fast that the carbon atoms literally get trapped inside the iron's crystal structure. This whole process creates a ton of internal stress, which is exactly what gives martensite its almost unbelievable resistance to wear and tear.
So you can totally see why martensite looks like a slam dunk, right? For rails getting absolutely pummeled by trains day in and day out, that incredible surface hardness seems like the perfect weapon against the relentless forces of friction and abrasion. On paper, it is the ideal candidate. And there it is. All of that internal stress that makes martensite so incredibly hard also makes it incredibly brittle. It has pretty much zero ductility, which means it can't bend or flex at all. Under the immense dynamic forces of a high-speed train, the weight, the side-to-side wobble, a rail made of pure martensite would just shatter. A catastrophic failure just waiting to happen.
So, if the absolute hardest material is a total failure, what's the answer? Well, engineers turn to a much more sophisticated, much more elegant solution. A material whose genius lies not in brute strength, but in a delicate, almost nature-inspired balance. Let's talk about the real hero here, Pearlite. Pearlite is just fascinating. It's what scientists call a two-phase nanocomposite. See, when steel is cooled at a more controlled, moderate rate, it forms these beautiful, alternating microscopic layers. And under a microscope, its structure actually resembles mother of pearl, which, believe it or not, is exactly where it gets its name. So here's the magic. It's how these two different layers work together. You've got layers of something called cementite, which are extremely hard and rigid. Think of them like microscopic armor plates, providing that vital wear resistance. But then, sandwiched in between, you have layers of a soft, flexible material called ferrite. This stuff acts like a built-in shock absorber, giving the rail the flex it absolutely needs to bend without breaking. Okay, but here's the thing. Just having Pearlite isn't enough. The difference between a standard rail and a super high-performance one comes down to one single critical factor that engineers can control with unbelievable precision. It's a secret that's hidden at the nanoscale. It all comes down to this: interlamellar spacing, or just SP for short. This is, quite simply, the physical distance between those hard layers of cementite, and controlling this tiny gap is the absolute key to unlocking a rail's ultimate performance. The science behind this is called the Hall-Petch relationship, but the concept is actually pretty straightforward. The closer you squeeze those hard cementite layers together, the harder it is for the soft ferrite layers in between to deform or slip. Those tight layers act like physical barriers, so tighter spacing equals exponentially stronger steel. Simple as that. And you can see exactly how this plays out in the real world. A standard, low-speed rail might have a spacing of around 300 nanometers, but the advanced alloys used for high-speed networks like the Shinkansen, they're in a whole other league. Engineers have shrunk that gap down to between 77 and 115 nanometers. That is a massive leap in nanoscale engineering. Let's just pause on that number for a second. 77 nanometers. That is unbelievably small.
We're talking about a level of precision that lets engineers create a material that is both incredibly hard and wear-resistant, yet still has the essential flexibility to prevent a catastrophic failure. I mean, this is really the peak of modern metallurgy. So, what does this all mean? Where have we landed? We started with the idea that brute strength was the answer, that the hardest material had to be the best. But we've discovered that the real solution is so much more elegant. It's a story all about balance.
And this is why it really matters. This sophisticated balancing act is what keeps high-speed rails from shattering. It's the invisible science that ensures the safety and enables the breathtaking speed of the world's most advanced trains. So the real takeaway, true strength isn't always about being the hardest. It's about intelligent design and the precise control of architecture, right down to the atomic level.
Just imagine a perfectly solid-looking piece of steel rail, one that's passed every single visual inspection, suddenly snapping like a dry twig under the weight of a train. Now, in the 20th century, this wasn't some what-if scenario. It was a terrifying reality that actually caused thousands of derailments. And the culprit? An invisible flaw, born from a single tiny element. And that killer, its name is hydrogen. Specifically, hydrogen gas getting trapped inside the steel while it's being made. This whole phenomenon is called hydrogen embrittlement, and for the longest time, it was one of the most unpredictable and, frankly, terrifying threats to railway safety. So you gotta ask, how on earth can this tiny little atom cause such a catastrophic failure? Okay, so this slide really breaks it down for us. Think about it like this. Molten steel is like a huge chaotic party room that can easily hold lots of tiny hydrogen guests. But as that steel cools and solidifies into this very ordered crystalline structure, the room shrinks dramatically. All those guests get forcibly kicked out, and where do they go? They all crowd into these tiny little closets, microscopic voids deep inside the steel. Once they're all packed in there, they team up, form hydrogen gas, and start pushing outwards with so much force that it literally cracks the steel from the inside out. And this tiny internal crack, it actually has a name. A hydrogen flake. It's this microscopic silvery disc, but its shape and its location make it the absolute perfect stress concentrator. It's like this little perfectly placed weak spot, engineered by accident, deep inside the metal where absolutely no one can see it. And that is the truly terrifying part. The rail looks perfectly fine on the surface, but with every single train that passes over it, that tiny internal flake just grows and grows, spreading like a cancer through the steel. It grows silently, invisibly, until that crack hits a critical size. And then, one day, under the load of just one more train, the remaining steel just can't hold on anymore and the rail snaps. Suddenly, violently, and with zero warning. So, okay, once engineers finally figured out this horrifying problem, that was step one. The next step was, how do we stop it? And this is where metallurgy had to evolve, moving from these slow, agonizing fixes to a near-perfect, high-tech purge. So the first crack at this, way back in the 1930s, was something called controlled cooling. Basically, they'd stick the hot steel in an insulated box and just let it cool down over several days. The idea was to give the hydrogen time to slowly sneak its way out. I mean, it kinda worked, but man was it slow, and it just wasn't good enough for today's high-performance steel. The modern solution? Vacuum degassing. Instead of letting the hydrogen casually walk out, we violently suck it out in a matter of minutes. But the vacuum is like a superhero with multiple powers, right? Not only does it suck the hydrogen content down to a super safe level, we're talking well below 1.5 parts per million. It also rips out other unwanted gases, like oxygen and nitrogen. This lets them do something called vacuum carbon deoxidation, which cleans the steel without having to use additives that could create brand new flaws. So what you end up with is this hyper-pure, incredibly tough steel that's perfectly primed for high-speed rail. All right, so we've purged the hydrogen. Problem solved, right? Well, not quite. That's only half the battle, because a modern rail has to deal with this massive paradox. It needs to have two completely opposite properties at the exact same time. No, really, think about this for a second. The top surface, where the wheel makes contact, that needs to be exceptionally hard to resist getting worn down by all that immense pressure. But if the entire rail was that hard, it'd be super brittle. It would just shatter from shock waves or thermal expansion or heavy loads. It has to be able to flex. So how in the world do you build something that's both rock hard and elastic? Well, the answer is just incredibly clever. It's a process of controlled cooling called deep head hardening. The idea is, instead of making the entire rail uniform, you create a perfect gradient of properties within the steel itself. It all comes down to mastering the cool down. And when I say mastering, I mean the physics here are wildly precise. As you can see on this chart, there's a perfect Goldilocks zone for the cooling rate. Cool it down too slowly, the surface is too soft. Cool it too fast, the steel becomes dangerously brittle. You have to nail that sweet spot, right between 3 and 6 degrees Celsius per second, to create that ultra-fine, ultra-hard surface you need. And to give you a sense of just how insane this is, the whole process starts with steel that's been heated to over 1,500 degrees Celsius. We're talking hotter than lava. And from that blistering inferno, engineers use what is essentially just jets of compressed air to cool the railhead at that perfect rate, about 4 degrees Celsius, every single second. That is an incredible display of thermal control. And what do you get for all that precision? You get a surface hardness clocking in at over 350 on the Brinell scale. That is an unbelievably tough, wear-resistant surface that's ready for all the punishment high-speed travel can dish out. But this, right here, is where the real genius kicks in. The jets of cool air, they're aimed only at the top of the railhead. And because heat moves pretty slowly through solid steel, the core of the rail gets to cool down at a much more relaxed pace. What you get is this incredible, seamless gradient, an armor-plated crown that gradually transitions to a tougher, more flexible core that acts as the rail's spine, absorbing shocks without cracking. So when you put these two huge breakthroughs together, getting rid of the hydrogen flakes and creating that perfect hardness gradient, what you have is more than just good engineering. It's really a victory on an atomic scale. You see, the reason we can have these incredible 400-kilometer-per-hour trains isn't just because of sleek aerodynamic designs. And it's not just about raw power or having ridiculously strong electric motors. No, it is at its very core a victory of atomic architecture. It's about meticulously engineering steel at the nanoscale, orchestrating the arrangement of atoms to create a material that can withstand forces that would just completely disintegrate normal infrastructure.
You know that sound, right? That classic, rhythmic click-clack of a train on the tracks? For more than 100 years, that was the sound of travel. But it's mostly gone now. So let's get into it and uncover the incredible secret science that silenced the rails and, in doing so, unlocked the future of high-speed travel. That's the key right there. That click-clack sound wasn't a feature, it was a bug. It was a necessary evil, the audible proof that engineers were in a constant fight with one of the most fundamental, most unforgiving laws of physics. And here's the big boss they were fighting: thermal expansion. It's simple, really. Things get bigger when they're hot and they shrink when they're cold, and steel is no exception. Now, that might not seem like a big deal, but when you have literally hundreds of kilometers of steel track baking in the sun, that tiny expansion adds up to a colossal problem.
So, to deal with this, the early railway pioneers came up with what seemed like a really straightforward solution. But as it turns out, that simple solution came with some really serious baggage.
What they did was what we call the short rail method. It makes sense, right? You just lay down shorter, manageable pieces of steel, one after the other. You join them together with some hefty bolts and plates, and this is the crucial part. You leave a little gap between each section. There was a pressure valve, a little bit of breathing room for the steel to expand on a hot day without turning the whole track into a twisted mess.
But here's where it all starts to go wrong. Every single one of those gaps created this vicious cycle. See, every time a train wheel rolled over a joint, it wasn't a smooth transition. It was a tiny, violent impact, a little slam. And that constant hammering again and again just beat up the ends of the rails, damaged the wheels, and of course, it gave passengers a terribly bumpy and uncomfortable ride.
And this is the real takeaway. Those gaps weren't just annoying, they were a physical wall. They put a hard cap on how fast we could travel. If you tried to go too fast over those joints, the vibrations would get so intense they could literally shake a train to pieces. If we ever wanted to go faster, we needed a smoother road.
So the solution was pretty obvious, right? Get rid of the gaps. The challenge was figuring out how to create a single, unbroken ribbon of steel that could somehow defy that fundamental law of thermal expansion.
And they actually did it. This is continuous welded rail, or CWR for short.
Thanks to welding tech that really took off around World War II, engineers could fuse those short rails into one seamless piece, sometimes for hundreds of kilometers at a time. This was it. This was the breakthrough that killed the click-clack and made high-speed rail possible. But in solving one problem, they created a brand new one, and this one was invisible and terrifying.
You see, by taking away the gaps, they didn't get rid of the thermal energy. It had to go somewhere. And if it couldn't physically move the rail, it turned inward, unleashing an invisible war of forces deep inside the steel itself. This is the whole idea behind restrained thermal expansion. The rail is now clamped down so incredibly tightly to heavy concrete sleepers and tons of rock ballast that it basically can't move at all. So all that energy that would normally make it expand or shrink gets converted. It becomes this immense, trapped, internal mechanical stress.
And this trapped stress has two very dangerous faces. On a freezing cold day, this steel wants to shrink, but it can't, so it's under an incredible stretching force. We call that tensile stress. The risk? It could just snap explosively. Then on a scorching hot day, the steel wants to expand, but it can't, so it's being squeezed with massive compressive stress. The risk there? The track can suddenly and violently buckle sideways, creating what's called a sun kink. Both are absolutely catastrophic. And just to give you an idea of the forces we're talking about, just look at this number. That's the modulus of elasticity for this steel. It's basically a measure of its stiffness, and it reveals the absolutely staggering pressures that this track has to silently fight against every single day.
So how on earth do you manage forces like that? How do you keep this ribbon of steel, hundreds of kilometers long, from tearing itself apart? Well, the answer isn't about fighting the force, it's about tricking it with an absolutely elegant piece of engineering. Here's the secret. The whole game is to establish a zero-stress state. Engineers figure out a neutral temperature, which is basically a happy medium between the absolute hottest and coldest temperatures that area ever experiences. The entire goal of the installation process is to lock that rail down when it is at that perfect neutral temperature.
This is called destressing, and there are a couple of ways they do it. The natural way is, well, you just unbolt the rail and wait. You literally wait for the weather to be perfect, for the rail to hit that neutral temperature on its own, and then you scramble to lock it all down. Or, more often, you use the artificial method. You bring in these massive hydraulic machines that literally stretch the cold steel to the exact length it would be at the neutral temperature, and then you lock it down tight.
Okay, so managing all this on solid ground is one thing. It's a massive challenge, but it's manageable. But what happens when that ground isn't solid? What happens when you have to lay this perfectly balanced ribbon of steel over something huge and, well, moving, like a suspension bridge?
This is where the complexity just goes off the charts, because now the thermal forces inside the rail are interacting with the bridge that is also expanding and contracting with temperature, swaying in the wind, and vibrating under the weight of the train itself. It's a physics problem layered on top of a physics problem.
And the solution, ironically, is to bring back the gap. But we are not talking about the old, crude joints from the past. Oh no. These modern bridge expansion joints are incredibly sophisticated pieces of machinery. They're more like complex shock absorbers, designed to handle forces from every possible direction at once. From heat, from a train slamming on its brakes, from the bridge itself bending, even from earthquakes.
And this number really shows you what we're dealing with. These modern joints can allow for 380 millimeters of movement. That's 38 centimeters. That's more than a foot of sliding displacement they can handle safely. It is an absolutely incredible piece of engineering, turning a simple old problem into a high-tech solution that lets us build railways in places we never could have before.
We're going to dive into the absolutely incredible science of how you take two separate rails and forge them into one continuous, unbreakable strand of steel.
I mean, just listen to that description. This isn't just about construction. This is high-temperature chemistry in its most raw and dramatic form. We're talking about a reaction so powerful, it literally reforges solid steel right there on the spot.
So how in the world is it done? That's the big question for this explainer. It's a fascinating process that's this wild mix of brute force and almost surgical precision. And the answer is a method called aluminothermic welding. You probably know it as thermite welding. To really get it, we're going to walk through 5 key stages. We'll start with the chemistry behind that violent reaction. Then we'll look at the crucial prep work that has to happen before the fire. We'll witness the inferno itself, understand the delicate art of cooling, and finally, see how that perfect, permanent joint is forged.
Okay, so at its very core,
This whole thing is a triumph of chemistry. It's all about one thing: generating an insane amount of localized heat very, very quickly to completely melt that super tough high-carbon rail steel.
But here's the catch. Before you can even think about lighting that fire, every single detail has to be perfect. All that spectacular chemistry, it's completely useless if you don't nail the setup with absolute, painstaking precision.
And the level of detail here is just incredible. The crew has to align the rails perfectly, grind the ends down to a mirror shine so there are zero contaminants, set a very specific gap, and even introduce a slight upward bend. That's called a camber. Then they clamp on a special heat-resistant mold and preheat the whole thing to keep the steel from cracking under thermal shock.
And that gap? It's not a suggestion. It has to be exactly between 26 and 30 millimeters. We're talking about a tolerance of just 4 millimeters. That's less than the width of a pencil, for a joint that's going to support thousands of tons.
So, why lift the rails by just 1.5 millimeters? It seems so tiny, right? Well, it's actually a brilliant calculation. It's designed to perfectly counteract the shrinkage that happens when thousands of degrees of molten steel starts to cool and solidify. Without that tiny lift, the rail would actually dip down, creating a critical weak point.
All right, the prep work is done. Everything is perfect. Now for the main event. It's time to unleash the chemical inferno that makes this entire process possible.
The science behind it is called an exothermic reduction-oxidation reaction. Okay, that's a mouthful. In simple terms, think of it this way. You have aluminum powder and iron oxide, basically rust. When you ignite it, the aluminum gets so greedy for oxygen that it violently rips the oxygen atoms away from the iron. This releases a blinding flash of energy and creates pure, liquid steel at around 2,500 degrees Celsius. And what's really neat is that the reaction produces two separate liquids. The heavy, pure molten steel is exactly what we want. It sinks to the bottom and fills the mold, forging that perfect molecular bond. Meanwhile, the lighter stuff, the aluminum oxide, which is just waste slag, conveniently floats right to the top, where it can be channeled away.
Now you might think, okay, the metal's been poured, we're done. But nope, the real engineering miracle, the make or break moment, happens completely out of sight. The true magic is all in the cooling.
How fast or how slow that molten steel solidifies is the single most important factor, period. It determines the internal crystal structure of that new steel, and that structure dictates everything: its strength, its flexibility, and ultimately, its lifespan. So you really have three possible fates for this weld. If you cool it too fast, you get something called martensite. It's incredibly hard, yeah, but it's also dangerously brittle. It could literally shatter. No good. If you cool it too slowly, the metal grains inside grow way too big, making the joint weak and soft. Also no good. The goal is that just right sweet spot that forms a fine pearlite structure. That's the perfect balance of strength and flexibility that you need to last for decades out on the track.
So once that critical cooling phase is managed, we hit the final stage, perfecting the joint, with some really advanced material science and a super rigorous finishing process.
You see, a standard thermite mix isn't always going to cut it. For high-speed lines or tracks that carry incredibly heavy freight, engineers use specialized alloy thermite mixes. These have microscopic additives, things like rare earth metals, that basically act as a cleanup crew inside the molten steel. They get rid of excess oxygen, and this part is so cool, they actually round off any sharp impurities, which stops tiny microscopic cracks from ever even forming.
And the difference is huge. You can see right here, these alloy mixes give you a weld with much higher hardness and much greater tensile strength. Now, there is a trade-off. You lose a little bit of flexibility, but for those really high-stress tracks, that extra strength is completely non-negotiable. But the weld itself doesn't exist in a vacuum. All that intense heat creates something called the heat-affected zone, or HAZ. This is the original rail steel next to the weld that gets baked but not melted. That heat actually alters its structure, creating a really complex and potentially dangerous zone with internal stresses and soft spots. And managing the HAZ is a massive challenge.
So to make absolutely sure the weld and that tricky haze are perfect, the joint has to pass one last rigorous exam. It gets meticulously ground down to match the rail profile exactly. Then it gets a visual inspection for any surface flaws, followed by hardness tests, and finally they bring out the high-tech gear, ultrasonic testing, which uses sound waves to hunt for any hidden voids or imperfections deep inside the metal.
And after all that, all the fire, the precision, the microscopic engineering, that brief,
violent burst of chemistry is now officially certified. It's a seamless, permanent part of our critical infrastructure, ready to handle millions of tons of traffic.
Have you ever thought about what it takes to lay a ribbon of steel across a continent? Now imagine that ribbon has to survive temperatures that would literally shatter normal metal. Today, we're diving into the incredible material science that allows China's high-speed rail to exist, let alone thrive, in some of the most punishing environments on the entire planet. This is a story of metallurgy on a truly massive scale.
And it all starts with this number, 70 degrees Celsius. Now that's not just the difference between a hot day and a cold one. That is the staggering annual temperature swing that the northern rail lines have to endure year in, year out. That kind of thermal stress is just designed to tear conventional infrastructure to absolute pieces. And this is what engineers were up against. They called it the Hinterland Gauntlet. You have to picture this, laying thousands of kilometers of hyper-precise track across a landscape that is actively, physically trying to destroy it through these brutal freeze-thaw cycles every single year.
And to really see this challenge up close, we've got to look at the Harbin-Dalian Line. We're talking 928 kilometers of rail that cuts right through China's northeast. This is a place where the ground itself freezes solid, swells up, and then thaws, trying to buckle and twist the tracks with it. It's the ultimate proving ground.
So the whole system is built on something called a ballastless track. You know the crushed rocks you see on old train lines? Yeah, this doesn't use that. It's a solid slab of concrete. Now that's amazing for the kind of stability you need for high-speed travel, but it also means the whole thing is one single rigid piece, and that concentrates every last ounce of stress from the temperature swings directly onto the steel rails themselves. So you end up with this fundamental dilemma. In the dead of winter, everything shrinks. The steel is being pulled apart by this incredible tearing force. But then, in the summer heat, everything expands, pushing outwards, threatening to literally shear the bolts and fastenings right off the track. It's being pulled and pushed constantly. So how in the world do you solve that? Well, you start with the backbone, the rails. You have to invent a steel that can handle being stretched and squeezed day after day for decades without giving up. And here it is. Meet the hero of our story, U75V steel. Get this, every single meter of this rail weighs 60 kilograms. That's like packing an entire person's weight into just 3 feet of steel. This isn't just regular steel. It's a specially designed alloy, built for one purpose, to win this fight against the elements.
Now the power of this steel is all in its recipe. You've got your basics: carbon for hardness, manganese for wear resistance, silicon for strength. But the real secret ingredient, the absolute game changer, is vanadium. So what's it actually doing? Well, think of the steel's internal structure like a bunch of tiny packed grains. Vanadium forms these microscopic particles that act like little pins, locking those grains together. It stops them from shifting around and deforming when the steel is under incredible stress. It's like a reinforcing skeleton on a microscopic level. But, you know, brute strength is only half the battle. This steel also has to put up with the endless, pounding impact of trains flying by at high speed. So it's not just about being strong, it's about being designed to fail, as slowly as humanly possible. And that brings us to this number, 515 megapascals. That's the steel's baseline fatigue strength. It means it can handle that insane level of stress for over 5 million cycles. That's like 5 million trains passing over it, before it even starts to show the first signs of getting tired. That's just incredible endurance. An amazing stat for sure, but here's the thing, no material is perfect. After all that punishment, over all those years, tiny microscopic cracks are going to start to form. It's inevitable. So, what happens then? Does the rail just snap? No way. This is where the steel gets really clever. It actually has a built-in self-defense mechanism. Check this out. As a train wheel rolls over, its immense weight crushes the metal grains right at the very tip of a tiny crack. Then, as soon as the wheel passes, that crushed zone kind of expands back a tiny bit, and that expansion physically wedges the crack shut, shielding the fragile tip and stopping it from ripping any further. The steel is literally slowing down its own death. Okay, so the rails themselves are unbelievably tough, but you have to join hundreds of them together to make a continuous track. And as any engineer will tell you, a chain is only as strong as its weakest link, and in this case, that weak link is almost always the weld. So to create those seamless rails, they use a process called flash butt welding.
They basically zap the rail ends with a massive electrical current to fuse them together. To do this, they actually use a slightly different steel, U71Mn. And the whole challenge was perfecting that weld. The solution, believe it or not, came down to a tiny, almost invisible change in the steel's chemistry.
So what was this huge breakthrough? This. A reduction in the manganese content by less than 0.1%. It's a tweak to the formula you would never ever notice just by looking at it.
And the result of that nearly invisible adjustment? A staggering 65% increase in the impact toughness of the welded joint. That is a monumental improvement from a microscopic change. And that right there is a core principle of material science. Tiny adjustments can lead to absolutely massive results.
So why does it work? Well, in simple terms, pulling back on the manganese just a little bit stops the steel from forming these brittle, almost glass-like structures as the super hot weld cools down. It also gets rid of these tiny, soft impurities, which act like microscopic weak spots, the exact places a deadly crack would love to start. All right, so the rails are rock solid. But what about the trains themselves? Remember, that same unforgiving environment that's attacking the track is also trying to tear apart the train cars riding on top of it.
The problem with the early train cars was that the aluminum alloys they were made from had a critical weakness. They were susceptible to metal fatigue, sure, but also to something called stress corrosion cracking. That's basically a nasty combo where physical stress and a corrosive environment team up to make tiny cracks form and spread.
So, the answer was a new, much more advanced aluminum alloy, A7NO1T5. And just like with the steel, the secret was microdosing the aluminum with tiny, carefully controlled amounts of other elements. In this case, things like zirconium and chromium, to totally change its core properties.
And this new alloy was a total game changer. I mean, it's incredibly strong. But the most important part is that its sensitivity to that dangerous stress corrosion was drastically reduced. That's what ensures these car bodies can actually survive their brutal journey, year after year.
And that really is the million-dollar question, isn't it? I mean, it's one thing to build an engine powerful enough to go that fast, but it is a whole other challenge to build a machine that doesn't just tear itself to pieces from the incredible forces at work. To solve this, the engineers couldn't just make a few tweaks. They had to go all the way back to the drawing board. This was a total, ground-up reinvention of what a high-speed train is supposed to be.
So on the surface, you see some really impressive but kind of expected upgrades. They tweaked the shape to slash aerodynamic drag by a whopping 22%. They managed to cut the train's total weight by 10%. And they brought in these super efficient new permanent magnet motors. But that last one, well, these new motors created a brand new and frankly terrifying problem. Here's the dilemma. A normal electromagnet, you can just switch it off. But a permanent magnet is, well, it's permanent. It is always on. So just imagine, you're flying down the track at 400 kilometers an hour, and there's a short circuit. You can't turn the motor off. It would just keep spinning itself into a catastrophic failure. The solution is just brilliant, a digital safety net. It's this incredible protection system that can spot a tiny fault, and in just 0.2 of a second, literally faster than you can blink, it reroutes all that massive electrical current and completely neutralizes the threat. Disaster averted.
But believe it or not, sorting out the electronics and the aerodynamics, that was kind of the easy part. The real breaking point, the problem that could have stopped this entire project dead in its tracks, was purely physical. It was the crushing, relentless stress on the wheels and the rails.
It all boils down to something so small. The entire weight and force of this multi-ton machine hurtling forward is concentrated on a point of contact between the wheel and the rail that's no bigger than a dime. At these speeds, that tiny spot gets hammered with intense, high-frequency stress that wants to tear the very steel apart. And this is exactly why the old materials just weren't gonna cut it. Our very best alloys, the super strong steel we use in jet engines and other high-speed trains, they simply give up. At these new speeds, the insane heat and vibration makes them soften and crack. They've hit their physical limit, period. So to get past this limit, scientists had to think way outside the box. They needed a full-on revolution in metallurgy, and what they came up with sounds like something out of science fiction. They're called high-entropy alloys. You see, for the last 3,000 years, the recipe for making a strong metal has been basically the same. You take a main metal, like iron for steel, and you just sprinkle in a little bit of other stuff to make it stronger or tougher.
High-Entropy Alloys take that 3,000-year-old rulebook and they just toss it out the window. Instead of one main metal, you take 5 or more completely different elements, things like titanium, tungsten, zirconium, and you mash them all together in nearly equal huge amounts. It's a complete rethinking of what an alloy even is.
And this is where things get really weird and wonderful. The secret to the unbelievable strength of these new alloys lies in something that seems totally backward. It's the paradox of chaos.
It all boils down to a fundamental law of the universe, entropy, which is really just a fancy word for disorder. When you mix all these different atoms together in huge amounts, you create this incredible amount of chemical chaos. And this chaos is so powerful that it actually overrides the natural tendency of atoms to form weak, brittle clumps. Instead, it forces them all into a simple, perfectly uniform, and unbelievably stable crystal structure. The best way to picture this is to imagine trying to build a perfect, neat pyramid using bowling balls, tennis balls, and marbles all at once. It's impossible, right? The different sizes would create this massive strain and distortion all through the structure. That's exactly what's happening inside this metal at an atomic level. And that internal strain, that's the magic ingredient. Scientists call it an atomic traffic jam. All that friction makes it incredibly difficult for microscopic cracks to spread. So when the wheel puts stress on the rail, this atomic traffic jam literally stops fractures in their tracks. The result is just unbelievable strength. And get this, at the point of impact, the structure can actually transform and harden on the fly, making it even stronger right where it needs it. Okay, so how in the world do you actually make one of these impossible alloys? You can't just melt everything together in a normal furnace. You need a manufacturing process that's just as futuristic as the metal itself.
The problem with the old way, just casting it, is that it's way too slow. As the metal cools, the different atoms have time to get picky. They start to separate, find their friends, and form these large, weak crystal grains that just ruin the whole effect. The solution? Lasers. Of course, it's lasers. They use a process called laser powder bed fusion, which is a lot like 3D printing with metal. High-powered lasers flash melt and fuse tiny bits of alloy powder, layer by layer. It happens so fast that the atoms are frozen in place before they have a chance to separate. And just look at the difference. The grain size plummets from a weak 200 micrometers down to a super strong 13.4. So, what's the final result? A compressive yield strength of over 2 gigapascals. Now, to put that in plain English, that means it is literally twice as strong as the exact same alloy made using old-fashioned methods. That's not just an improvement, that's a quantum leap. So, next time you see footage of the CR450 blurring past the countryside, it's easy to focus on the sleek aerodynamics or the powerful motors. But the real breakthrough, the true hero of this story, is completely invisible. The researchers who developed it put it perfectly. They called it the silent metallurgical foundation. It's this mastery over chaos, forged by lasers, that allows this incredible machine to ride safely and smoothly at speeds that, until now, were physically impossible. The way a nation designs its high-speed rail, I'm talking about the metals they choose, the way they distribute weight, all of it reveals this deep set of priorities. Priorities shaped by their geography, their history, and a totally unique engineering philosophy. So let's start with the pioneer, the OG of high-speed rail, Japan. Their entire approach is defined by one core concept, this almost obsessive desire to be gentle with their tracks. I mean, try to put yourself in their shoes back in 1964. Japan's engineers were literally writing the rulebook from scratch. They were building a super fast train line through a crowded, earthquake-prone country, and get this, they had to build it on track beds that were nowhere near as strong as the ones we build today. So here's the crucial point. Facing all those challenges, they made a fundamental choice. Instead of trying to build impossibly strong tracks, which was really difficult, they decided to build an incredibly light train. The whole goal was to protect the infrastructure they already had. And this right here perfectly illustrates their strategy. You see, instead of one single monstrously heavy locomotive pulling everything, they put small motors on pretty much every single axle. This is the electric multiple unit, or EMU. It spreads the train's weight out perfectly. It's like laying down a fine layer of dust instead of dropping a heavy rock.
And they went all in on this philosophy. We're talking ultra-lightweight aluminum parts. And they use something called regenerative braking. It's kind of like an electric car. When you slow down, the motors that power the train actually run in reverse, acting as brakes and generating electricity at the same time. This is genius because it not only saves energy, but it lets them get rid of tons of heavy mechanical brake parts. The result? Barely any stress on those steel rails.
All right, so that's Japan. Now let's jump over to China and see how they built a completely different approach. They saw what Japan did, and then they went in a starkly opposite direction. You have to understand, China's problem wasn't about preserving old tracks in a small country. Their mandate was to conquer a continent. They had to connect a massive population across immense distances and through some of the most punishing terrain on Earth. And crucially, they were building on brand new fortress-like foundations. Because their modern tracks could handle it, their philosophy became one of strength and resilience. They didn't need to be delicate. They needed their trains to be tough, durable workhorses, capable of carrying huge numbers of people, day in and day out. And you can see this difference just by looking at the train's composition. While Japan puts a motor on practically every axle, China often uses these mixed sets, with some cars being unpowered trailers. This makes the train heavier overall and concentrates force on the tracks, the exact opposite of the Japanese model. But this isn't a mistake. It's a very deliberate choice that enables something else. So why would you allow that extra weight? For raw stopping power. Those heavy, unpowered trailer cars provide the space and the structural support for massive, high-friction mechanical brakes. To safely bring a heavy train to a halt from speeds approaching 400 kilometers per hour, you absolutely need that brute force. The extra weight is a necessary trade-off for performance at those extreme speeds. And when you put it all side by side like this, the contrast is just stunning. It crystallizes everything, doesn't it? On one side, you have Japan's feather-light preservation. On the other, China's brute permanence. Two different problems, two brilliantly engineered and totally opposite solutions. But the story doesn't end there. Japan's obsession with efficiency and lightweighting has led to one of the most remarkable sustainability stories in modern engineering. It's a fantastic little coda to their story. For years, it was basically impossible to recycle the high-grade aluminum from old Shinkansen bodies because of all the paints, the glues, and the steel contaminants. But now, through these advanced chemical processes, Japanese engineers can strip all that away, recovering pristine aerospace-grade aluminum to build the next generation of trains. And get this closed-loop recycling process slashes the carbon dioxide emissions from manufacturing a new train body by an incredible 97%. 97%! It's just a testament to their deep national commitment to efficiency. So, the big thing you should take away from all this is that there's no single right way to build a bullet train. It's absolutely not a one-size-fits-all science. What we really see here are two masterclasses in problem solving. Japan's system is a perfect solution for its context. China's system is a perfect solution for its context. They are both engineering marvels tailored precisely to the needs of their nation.
And this is a really serious question. When you have a massive project like the Hainan Ring Island High-Speed Railway, you're building a marvel of engineering in a place that is actively trying to tear it down. So how on earth do you keep people safe on trains going at blistering speeds when the very air is corroding the tracks right out from under them?
Because the enemy here, it's not something obvious like an earthquake. No, the real enemy is something you can't even see. It's this constant, microscopic mist, a nasty combination of insane humidity, intense heat, and a never-ending barrage of airborne salt. It is, quite literally, the perfect storm for corrosion.
So, to really get how we fight this thing, we first got to understand the attack itself. Let's break down what this invisible mist is actually doing to solid steel on a chemical level.
Okay, so this is basically a full-on molecular assault. First, that salty mist, which is just loaded with chloride ions, settles on the steel. Now, these ions are tiny, but they're incredibly aggressive, and they punch right through the steel's natural protective oxide layer. Once they're in, they act like a catalyst, kicking off something called anodic dissolution, which is just a fancy way of saying the iron itself literally dissolves. This creates these deep pits, hollowing out the steel from the inside and creating perfect weak spots for a catastrophic failure down the line.
So when you're facing this kind of relentless chemical attack, what can you possibly do? Well, metallurgists turn to a surprisingly elegant solution, a kind of unlikely hero in the world of heavy industry.
And here they are, cerium and lanthanum. These are rare earth elements. And what's absolutely wild is that you only need to add microscopic amounts to the molten steel when it's being made. It's this tiny little tweak to the recipe that completely changes the game.
Now this whole protective process actually has two parts. And the first line of defense isn't out there on the coastal tracks. Nope, it's forged way back in the roaring heat of the steel mill itself. To get this, we need to know what a deoxidizer is. It's basically something you add to molten metal to clean it up, to pull out unwanted oxygen and other junk. And it just so happens that rare earth elements are fantastically good at this. They have this immense chemical attraction to oxygen and sulfur. They're just way better at the job than the traditional stuff. So when you inject cerium and lanthanum into that liquid steel, they basically go on a search and destroy mission. They aggressively hunt through the molten mix, grabbing onto and neutralizing all these nasty little impurities you really don't want, things like titanium, lead, arsenic, you name it. They literally purify the steel from the inside out. And here is where you can literally see the difference it makes. On the left, in normal steel, those soft impurities get stretched out into these long, sharp, needle-like shapes. They're basically tiny internal cracks just waiting to happen. But on the right, with the rare earth steel, look at that. The compounds they form are incredibly hard and stay as perfect little spheres. They don't deform. This keeps the steel's internal structure solid, making it way less likely to crack from the inside.
So that internal strength, that's the first line of defense. But the true mastery here, the real magic, happens when the finish rail is actually out there, exposed to that corrosive sea air. This is where the self-healing atomic shield comes into play.
To get this, you have to know that not all rust is created equal. You've got bad rust, gamma FeOH. Think of it as flaky and weak. It falls off easily, always exposing fresh metal to attack. And then you have good rust, alpha FeOH. It's the complete opposite, super dense, totally stable, and it actually forms a protective barrier.
So here's the incredible part. As the steel inevitably starts to rust in the salty air, those rare earth atoms that are embedded inside it get to work. They actively manipulate the chemistry of the rust itself. They literally force the bad, flaky rust to change its molecular structure and transform into the good, dense, protective kind. And this amazing process leads to what the researchers call an active polarized rare earth atomic shield. What that means is the cerium atoms physically move and line themselves up right at the boundary, right at the interface between the raw steel and that new dense layer of rust they just helped create.
So how does this shield actually work? Well, first, those cerium atoms form this special polarized layer. This layer acts like a superglue, dramatically increasing the adhesion and locking that good rust layer permanently onto the steel. And the result? The pathways for those destructive chloride ions are just completely shut down. The whole corrosion process just grinds to a halt.
Now this all sounds amazing on a microscopic level, right? But does it actually hold up in the real world? Well, the final proof is in the engineering tests, and the results are pretty stunning.
Check this out. This chart shows what happened in a super aggressive salt spray test. It's meant to simulate decades of coastal exposure in a short time. The bar on the left is standard steel. You can see a ton of it just gets eaten away. But the bar on the right, the rare earth steel, I mean, wow, the difference is just night and day. And it's not just about losing less weight. The electrochemical tests show a massive positive shift in the steel's potential not to corrode. This is a hard number that proves the steel itself is just fundamentally more stable and resistant to self-destruction. So the bottom line is, by engineering steel right down at the atomic level, we get a final product that can actually withstand some of the harshest environments on the planet. We get high-speed tracks that are stable, sound, and basically immune to what the source material beautifully called the invisible electrochemical fires of the ocean. And that's really the power of modern material science. It leaves you with this really cool question. If we can teach steel to build its own armor against the ocean, what other invisible fires, say in medicine or energy or computing, are out there just waiting for us to conquer them atom by atom?